Hello everyone, I am Debabrata from IIT Guwahati. Today I am going to present our work HMDS, a Makespan minimizing DAG scheduler for heterogeneous distributed systems. It is a collaborative work with Arnav Sarkar and Chandan Karfa. These are my outlines. A cyber-physical system is an integration of two subsystems. A cyber subsystem is often a heterogeneous distributed system, and a physical subsystem consists of electromechanical components. Applications in today's cyber-physical systems are often model-less tasks. Nodes represent tasks, edges denote dependency among tasks. Let me formally define the problem statement. Given an application DAG, a fully connected platform of heterogeneous processors, the scheduling objective is to determine the execution start times and processor assignments for all tasks such that the Makespan is minimized while satisfying resource and precedence constraints. A few state-of-the-art wars listed here, out of which HEFT and PFT are most popular and well-known algorithms. This work proposed two algorithms, HMDS-BL, a list scheduling algorithm, HMDS, a depth-first branch and bound based search technique, which is an extension of HMDS-BL, is equipped with a set of novel tunable pruning mechanisms which allow the designer to obtain a judicious balance between performance and solution generation times, depending on the specific scenario at hand. The HMDS-BL algorithm consists of two phases, task prioritization phase and processor selection phase. In task prioritization phase, we compute two parameters, predicted finish time and a rank list. The rank list detects the order by which tasks are going to execute in processor selection phase. For each task, a processor is allocated and an actual start time is allocated during the scheduling. PFT of task J on PN provides an estimate of total time required to complete the execution of all dependent nodes of task J, assuming tau J to be allocated for execution on processor PN. Then we calculate the rank PFT is an average of tasks on all processors. Now we create a rank list called task list, which consists of all tasks in non-increasing order of rank PFT value. Now we select one task from the rank list and go for the processor selection phase. In processor selection phase, for each task we compute effective start time, effective finish time and optimistic finish time. For example, the effective finish time of task 9 on P2 processor can only be started after all its predecessors completes its executions and their outputs reaches to the task 9 on P2 processor. So the EST of tau 9 is 74. The EFT of tau 9 is 74 plus its execution time is 129. Then we calculate optimistic effective finish time, OEFT. OEFT is the summation of EFT plus PFT values. Summation of EFT and PFT value. OEFT task J on PN provides an estimate of the exit task completion time relative to the effective execution finish time of the current task tau J on PN. Finally, the task is allocated to a processor on which the OEFT value is minimum. So task 9 is assigned to processor P2. Finally, we compare HMDS-BL with HEFT, PFT, PALG, PPTS and PSLS and found that HMDS deliver better result as compared to all these algorithms. In HMDS-BL, for a fixed rank order, Each task has mod P heterogeneous processor choices during allocation. So the total number of possible distinct solutions for task set of size mod V is mod P to the power mod V. To search over the solution space, we devise HMDS, a depth first branch and bound search technique. For this example, HMDS deliver 177 Makespan, which is much lower than HMDS BL. Let's illustrate HMDS with a simple example. We have 4 tasks and 3 processors, so our solution space is 81. An experiment to bound the number of processor choices for each task to a small constant. We have seen that when we move from processor choices 1 to 2, we have seen a 7.4% reduction in average schedule length ratio, whereas when we move OOPS value 2 to 3, we only receive 0.19% reduction in schedule length ratio. But we have not received any changes when OOPS value moves 3 to 4. On the other hand, the algorithm required exponential runtime varying OOPS value 1 to 4. So we have decided here to fix the OOPS value to 2. When OOPS value is 2, the number of solution space is 16. Let PDES be an array of size OOPS such that OEFT tax on PDES 1 is less than 2 OEFT tax on PDES 2. So each tax has two options, PDES 1 or PDES 2, and we have 16 number of possible choices for 4 tasks in 2 processors. So initially we allocated all tasks to the PDES 1 processor, where the OEFT tax J is minimum. Let's begin. Task 1 is allocated to PDES 1, which is actually P3 processor, and for task 1 on P3, the OEFT value is 76, and when it allocated, its actual finish time is 32. Minimum schedule length ratio is initialized to infinity, and limit is 83. Limit is a value which is 10% of 76 for this example. Limit tells that whether we can go for the second minimum OEFT value for a tax or not. If OEFT value is less or equal to 83.6 or the limit, then we can explore the branch for a tax in the second best processor, otherwise not. We'll see later. Now task 3 is allocated to P3 processor, task 2 is allocated to P1 processor, and task 4 is allocated to P3 processor. At the end we got 84 is our schedule length. Next we try in depth first branch and bound technique. Let's task 4 in PDES 2 processor, and we found that the Makespan is 86, which is greater than to the best known Makespan 84. So mechanism according to mechanism 1, we prune this branch. Similarly, we prune this branch also according to mechanism 1, and according to mechanism 3, we prune this branch. Here 89 OEFT value of task 3 on PDES 2 value is greater than to the limit, so we prune this one. Then we explore task 1 on PDES 2. We found 80 is the OEFT value and 83.6 is the limit value. It is less, it satisfies the condition, and AFT is also less than best known Makespan. It is also satisfied. So task 1 is allocated to P1. Similarly, task 3 is allocated to P1. Task 2 is allocated to P3, and task 4 is allocated to P3, and we got a Makespan is 80, which is the current best Makespan for this schedule, and we pruned the next branch using the pruning mechanism 1. Using pruning mechanism 2, this branch is also pruned. Using pruning mechanism 1, this branch is also pruned. So by exploring the 16 possible solution, we found 2 solution, and we are successfully pruned all the branches here. In addition to that, we also use fourth mechanism to terminate the search based on the amount of time consumed with respect to that taken by HMDS BL. We also evaluate our algorithms using 2 benchmark task graph, Gaussian elimination and epigenetics, and we also use randomly generated task graph. The primary performance matrix is schedule length ratio. We pairwise compare the Makespan comparison of the scheduling algorithms, and we found that HMDS is perform more than 80% better solution as compared to other algorithms. This experiment is carried out by varying SLR for Gaussian elimination, and we found that HMDS is comprehensively outperform all the algorithms, whereas HMDS BL perform marginally well. The similar trend also achieved for epigenetics. In conclusion, the experimental result says that HMDS comprehensively outperforms state-of-the-art algorithms such as HEFT, PEFT, PSLS, etc. in terms of achieved Makespan, whereas HMDS BL is also able to perform better than these algorithms. Additionally, a prototype real-time platform implementation and a real-world case study on traction control application has been carried out to exhibit the practical applicability of the proposed work. As part of future work, researchers may utilize the generated lower Makespan of the proposed algorithms to optimize one or more performance matrices such as energy, cost, security, etc. in real-time system. These are few references. Thank you.